So far we've talked about energy and work in the work-energy theorem, and today we're going to extend that and talk about the energy stored in a gravity field, which we call gravitational potential energy, and the energy stored in a stretched spring or rubber band. That's called elastic potential energy. These are the ways we store energy mechanically. So let's review a little bit. Remember what energy is. Energy is the capacity to change the environment. If something has energy, then it can change the environment. And again, let me know if I get over this one. All right. Now, we talked about how energy is transferred from one system into another. We called that work. Work isn't really energy, although it's measured the same way energy is measured. Work is when energy is flowing in the environment from one system into another system. It's being transferred. Energy transfer through the application of a force. So if we applied a force to an object, I can do work on it. And by doing work, I'm transferring energy. And we said that that work is equal to the amount of force times the amount of displacement times the cosine, let me not use x's for that, force times displacement times the cosine of the angle between the force and displacement vectors. This is going to be really important here in a second. Okay. Now, one thing we found out is that if we look at the work, well, we're still in review here, so let's talk about the work energy theorem. We said that if the work being done is being done by the net force, that is the net force times the displacement times the cosine of the angle between the net force and the displacement, that will result, the result of doing that, the work or the energy that's transferred will change the kinetic energy of the object that work was done on. Now, a change in kinetic energy can be negative. If an object is moving really fast and I catch it, I slow it down, I take away its kinetic energy. I did negative work. Or if I throw a ball or something, I apply a force times the displacement and I add kinetic energy to it. And kinetic energy, of course, we did a little derivation, and I'm not going to repeat that derivation here. Go back and look at the other video. But it's equal to 1/2 the mass times the velocity squared of the object. So if I do work on an object, a force times displacement times cosine of the angle, and that force is the net force that's doing that work, well, the result of that will be giving it kinetic energy. It has mass and it has speed. And the thing about it is that once something has speed, now it can in turn do work, right? If something is moving at you really, really fast, that thing can do work, can affect change. You can apply a force through a distance. When you catch a ball that has lots of kinetic energy, that ball, when you catch it, it applies a force through a distance on your hand. So you do work on the ball does work on your hand. Okay? And so anyway, that was the work energy theorem. Now we're going to look at a way that energy is stored in the environment. And in a way, kinetic energy is energy stored in the environment, right? If something is moving really fast, if it has mass, it's moving really fast, that 1/2 mv squared tells you how much energy that object has. That energy is kind of stored up in the motion of that object. But there are other ways of storing energy, and one of them is gravitational potential energy. Gravitational potential energy. And I'm going to give it PE. I'm going to try to stick with the book that we use, PE for potential energy. By the way, a lot of books, and what we do in AP Physics C, as we call it, is called capital U. All right, so, and I have to find out what variables the AP test actually uses. So, but anyway, our book uses PE for potential energy. Other books use capital U, and it's just tradition. It's just what people decided to do. There's no, whatever. So we need an expression for that. Now, what is gravitational potential energy? It's the work that gravity can do because an object has mass and height. Now here's a really sad example. I would never do this, okay? But it just adds a little drama, okay? Suppose here's the floor. And here's my neighbor's cat, who is constantly pooping in my backyard because they don't take care of their cat. This makes me angry. And when I get angry, sometimes I have evil thoughts. And in this case, my evil thought is to catch this cat asleep in my backyard and then hold a bowling ball above the cat. Huh? I do. I dream. I will say again, I would never actually do this, but you know that person who cuts you off in traffic? Don't you have like dreams of having like an Exocet missile or something you could just take? Yeah, I do. I do too. Yeah. But I don't act on it. Yes. I'm a civilized person. All right. Now, would you agree that this bowling ball, which has mass, let's say it has a mass of 5 kilograms. That's a medium-sized bowling ball, actually. Mass of 5 kilograms. Do you think that this bowling ball, if I'm holding it over this cat, can it change the cat? Yes. So it has energy. But just as we figured out how much energy something had because it was moving by how much force through a displacement, and give us, we define gravitational potential energy the same way. And it's how much work can gravity do? Well, we're going to give this the balls can fall a certain height. Okay. And now, and this is all very intuitive, right? If you drop this bowling ball on your foot's going to change, right? There's energy stored in that bowling ball. But how much energy? Well, how much work can gravity do? Well, the work done, we said work is equal to a force times the displacement times the cosine of the angle between them. This is our basic definition, and we are going to use it. Well, if I release the bowling ball, what's the force acting on the bowling ball? What force is going to do work? This is a free body diagram of the bowling ball. There's only one force acting it after I release it, and that's the force of gravity. And the force of gravity is equal to the mass of the ball times the strength of Earth's gravity field near the surface, which is 9.8 newtons of force for every kilogram of mass. Yes? You with me?
Yes.
Okay, now, so when I figure out how much work gravity can do, I'm going to put an mg right here because that's a force. Okay, now what's our delta x? The way I've drawn this. From here to the cat, I'm going to call that height. Some people call it y. Some books use the letter y. Some use the letter h. You can even use x if you say, oh, x is up and down, but that can get confusing. So I'm just going to say h for right now. Now, times the cosine of, now, let me ask you this. If I release the bowling ball, it's going to fall down. So the direction of the displacement is down. The force is down, right? What is the angle between down and down? Yeah. 0 degrees. And what is the cosine of 0 degrees? 1. So this is just 1 times 1. So this is the work that gravity can do because something has mass, it's in a gravity field, and it has height. Okay, so we're going to call this potential energy. Now I'm going to put a little subscript on it, little g, spells peg. Okay, a little g. And what does that g stand for? Gravity. There's always somebody out there. Okay, and this is going to be equal to mgh. So this is our height, and h is our height above the reference. Okay? Now, so anyway, this is our basic equation for gravitational potential energy. Now I need to go a little bit faster here, so I'm just going to tell you a few things that, let's say that you want to climb a mountain. So here's sea level or whatever, maybe Mount Diablo or something. Oh, thank you. And so here's some kind of mountain. And here's the peak. And you're down here and you got your backpack on. And you're ready to go. So, you're going to have to do work to add altitude to yourself. And so we do this, we huff and puff, but oh, it's too steep right here, so we take a switchback trail and we go up like this. Oh, it's nice right here on this ridge. We go down a little bit, and then we get up here, and oh, we have to go back on these switchbacks, and then we get to the top. Okay, now let me ask you this. How much potential energy did I gain? What's the potential energy at the top? Well, it's my mass times the gravitational field times the height. It doesn't matter what path you take. To get from here up to here, all right, now you've added gravitational potential energy, and it does not matter what path you take. You could wander around this mountain all day and then get to here and then take a helicopter ride and then have them drop you off on the top. But if you get to the top, the work you did against gravity is the same. It's independent of the path. Now, of course, your body expended more energy as you hiked all around, up and down, because you're generating a lot of heat. And the human body is not 100% efficient. You're not going to turn 100% of your body's chemical energy into the change in height. In fact, most of that energy that you expel is just going to be into warming up air molecules all around you. But you will gain gravitational potential energy. And it doesn't matter how long the path is to get there. All that matters is how much height you gained. Okay, and that's gravitational potential energy. And so this is our basic equation for it. We're quite often going to deal with changes in potential energy. Well, that's going to be your weight times your change in height. Okay, now notice that a change in a height can be negative. Oh, by the way, height can be negative. What if, you don't have to change your notes or anything, but what if well, never mind, I'm not gonna, we'll worry about negative potential energy later. We will get to it. Now, kinetic energy is always positive. 1/2 mv squared is always positive. But gravitational potential energy can be negative if you're below. Okay, I'll go ahead and do it. Suppose, here's our cat. Here's a rat. A rat. Now the rat is at the bottom of the hole. So compared to the reference, the rat has negative gravitational potential energy. That is, the work done by gravity to get from here to where we measure height from, well, gravity is down, but the displacement would be up. So the cosine of 180 degrees is -1. So we're actually going to be doing negative work. That means that just means if gravitational potential energy is negative, that just means we're below our reference. So I got to do additional work just to get to 0. See this bowling ball right here? Somebody had to do work to lift the bowling ball up. So somebody had to transfer energy from their body into the bowling ball by lifting it up. Now that energy is available in the bowling ball because of its position in the gravity field. And we can do things with that energy. Okay. Now we're going to get to elastic potential energy, and this is a little bit more complicated. And I'm going to call this PE sub E, little e, for elastic. Well, this is the energy that I get. Here's a little spring. And I'm going to pull on this spring. Okay, so, yeah. So at first, it's really easy to stretch the spring. It doesn't take much force. But the more I pull on it, the harder it is to stretch. And now we're going to, in this class, we're going to use what are called linear springs. And a linear spring is one where when you plot the force it takes to pull on it, or the force that the spring pulls, is directly proportional to how much you stretch it out. Okay? So, so if I were to take a spring and plot the force on it, well, here let me draw a picture of it. So here's the spring. It's got a little tab on it or something. And here it's relaxed. So we're going to call this position 0. And we almost always, when we're dealing with springs, we almost always define the origin of our position axis as being where the spring is relaxed. It just makes the equations a lot easier to deal with. It's just like the starter we did, isn't it? Now, but the starter we did, we measured the force that we applied to the spring. But now we're going to deal with the force that the spring applies to the object. So let's suppose that I stretch this all out, and let's say I've got a crate right here on wheels. And this spring, we've taken this and we've stretched this out and we've hooked it on to this guy. And we want to know. So the elastic potential energy is the work, the spring. Now it can be a spring, it can be a rubber band, it can be any elastic material. That's why we call it elastic potential energy, because it's not just springs. But it's the work the spring can do because the spring has been stretched. Now, some springs you can also do the same thing if you compress it. Now, this spring right here, it's so tightly wound that it can't be compressed. So all we can do is stretch it. But there are some springs where you can squish them in or out, and within a certain range or certain domain of X, you know, they can push out or push to the left or push to the right. Now, what I'm going to do is take a look at this object right here, and let's say, how much work can it do? Well, the force, so the work is equal to the force times force times displacement times the cosine. Wait a minute, something's wrong here. Something's wrong here. I mean, I can do this, but here's a problem. Oh, actually, I'm going to do it like this. The oh, I see what I'm doing. Okay. Hold on a minute. I'm just going to do the magnitude of the force. This is the force that the spring applies to the object. And that's right, we do graphs where we do this, we're just dealing with it. This is our position X. So 1, 2, 3, 4, 1, 2, 3, 4. Yeah, and we'll make this in newtons. Now, I'm just going to make up some data. 10, 20, 30, 40. I'm just making up data here. Let's say at 1 meter, 2 meters, 3 meters, 4 meters. I'm going to keep this super simple. At 1 meter, the spring was applying let's make this more realistic. I'm going to add a 0 to all these. 100 newtons. But if I stretch it 2 meters, it's 200 newtons. And 3, it's 300 newtons. And 4, it'll be 400 newtons. Okay. Now, so I'm holding this thing out here. I'm holding this thing right here, and I want to release it. And the spring is pulling it to the left with 400 newtons of force. But when I release it, what is the force at 3 meters? 300. So the force that it's pulling on it is getting less and less and less and less until it reaches 0 when you get to the center. So you can't just say 400 or 400 newtons times 4 meters. If you do, you've got twice as much work as it's actually been done. What you have to do is you have to figure this out. The slope. So the work, the area equals 1/2 the base times the height, which in this case is 1/2 the base is 4 meters, and the height is 400 newtons. So you can see here that the work done is 800 joules, right? That's how much work was done. But what I'd like to do is get to an equation. So here's how we're going to do that. Let's figure out what's the slope of this line right here. It's each meter I gained 100 newtons. So it's 100 newtons per meter times x. This is the equation of the force that the spring applies as a function of x. Does everybody see that? Now I'll save the negative sign for later. This right here is a measure of how stiff the spring is. That is, if you want to stretch it 1 meter, you're going to have to apply 100 newtons of force. What if I want to stretch it 3 meters? Well, then it'd be 300 newtons of force. What if I wanted to stretch it 1/2 meter? How much force would I need? Yeah, 50 newtons. So this tells us how stiff the spring is. And this is called the spring constant. And we use a lowercase k to represent it. Lowercase k stands for the spring constant. It has units of newtons per meter. Now I'm going to do a little trick here. I want an expression for the energy stored up in a stretched spring. How much work can it do? Well, we said that work, it's the area of this graph, 1/2 the base times the height. Well, it's 1/2. Now, what is the base? Well, the base we're going to call x. And what is the height? Well, the height is the force. Everybody agree with that? Okay. But what did we say the force is equal to? Or the magnitude of the force that the spring applies is equal to kx. K is the spring constant times x. So I'm going to substitute that in here. One half x, that's 1/2 the base times the height, but the height is equal to kx. So this gives me 1/2 kx squared. This is the work that a spring can do because it's been stretched or compressed. It works for compression as well if you have a spring that will allow that. From the and x is the distance from the equilibrium position. So the work that a spring can do, because it's been stretched or compressed by a value x, we call elastic potential energy. So elastic potential energy is equal to 1/2 kx squared. But what you have to know is that this k right here is a property of the spring. It's the spring constant. And this really only works for what we call linear springs. There are some springs that don't behave in this nice, beautiful linear fashion here. So you can't really use this equation for nonlinear springs. But in this class, we're going to assume that springs are linear. And so now we've got, well, we're almost done. We've got an expression for, let's summarize here because we're almost done. If you want to know how much energy is stored in a gravity field, well, we call that potential energy of gravity, and that's equal to mgh. If you want to change in the potential energy, you go mg delta h. That'll work. Oh, I'm going to have to actually teach something slightly new. If we have the elastic potential energy, it's equal to 1/2 k x squared. Now, if you have a change in elastic potential energy, I'm gonna put something down here, and I don't want you to write it down because it's wrong. People will do this all the time. 1/2 k delta x squared. No, bad student. No biscuit. All right, so what you have to do is you have to say, okay, this is the final position squared minus 1/2 k, the initial position squared. So to figure out the change in potential energy, you'll have to do this. 1/2 k, it's x final squared minus x initial squared. Now, here's the thing. Delta x squared is equal to x final squared minus 2x final x initial plus x initial squared. Remember the FOIL thing? Well, this does not equal this. So I probably screwed you up by even mentioning it. It's okay, I kind of enjoy doing that. All right. So anyway, make sure you can attempt the homework problems using these ideas of energy stored. There's a little bit more to it. We'll get to it next time. That is all.